want to now talk about effusion, a topic related to our discussion of gas mixtures.
So gas molecules move randomly, and so one of the very important properties of gases is that they can expand into new volumes. This is very unique among gases. Solids and liquids don't do this, right? If you have like water in a bottle, it doesn't just fill the entire bottle, it only stays at the bottom of the bottle. So gas molecules can necessarily move, and if you give gas the ability to move into empty space, they will take that advantage of that. And so there's two different ways that that can happen. One, if you have an empty space, so you'd have, say, a sample of gas in, say, this part of the tube, and then there's empty space on this side. And so the question is, do you fully remove what's blocking it? In which case we call that process diffusion, where the gas just fills the entire container spontaneously. Or do you cut a little hole in your partition, in which case the gas has to pass through that hole, which is what we call effusion. Okay, so diffusion is, just kind of when you open it up, gases expand. We could think about all gases do expand to fill the volume. What we want to focus in on, though, is this idea of effusion. Okay, when we open up a small hole and allow gases to pass through that. And the hole is generally much smaller than, say, the entire surface of the wall that the gas is colliding with. Okay, so this is the passage of gas molecules through a small hole into, and this is important, an empty volume. Okay, so the gas molecules are just kind of bouncing around. Effusion is slower than diffusion because you have basically this small passageway. It's not necessarily that molecules need to fit. Gas molecules are tiny, right? Molecules are really small. These holes could just be like the size of like your finger, and you would still have effusion. Okay, and the point is that the molecules just have to hit just the right point on this big wall, right? There's a lot of other wall that the molecules aren't hitting in order for them to pass through. So effusion is just restricted in that sense going into this new space. So Graham's law of effusion says that effusion rates of gases are inversely proportional to gas molecule mass. And so what that would mean is that if a molecule is heavy, it effuses more slowly. So when we say heavy molecules, what we're talking about is molecular mass. So remember we talked about formula mass, get those AMUs. That'd be like the numbers on the periodic table, similar to, say, molar mass. Similar idea. Is the molecule really heavy? Is there a lot of mass in the molecule? And so effusion may seem kind of silly, right? Why do we care about these molecules moving through a hole, some sort of pinhole into an empty space? The reason why this is important is that this is the first property of gases that we've looked at that depends on what the gas is, right? Ideal gas law, Boyle's law, Charles's law, Dalton's law of partial pressures, combined gas law, all the basis of all of those ideas is that you don't care what the gas is, right? You just don't care because all gases respond and behave in the same ways. This is the first time we're seeing that it matters what the gas is. It matters, is your gas have a heavy molecule, because it's going to affect effusion. And so what that means is if you have two different samples of gas, two different types of gas, and you allow them to effuse, a lighter gas will effuse more quickly. And so effusing more quickly means, to say you have your helium and your ethylene oxide. Ethylene oxide is quite a bit larger. Helium's just helium, atomic number 2, atomic mass of 4. Whereas ethylene oxide, you got the 2 carbons, oxygen, and some hydrogens. There's a lot in there. So say you opened up these holes at the same time, you can see that because the helium effuses more rapidly, more of those molecules have made it into the empty space than the ethylene oxide would. So over time, it's faster for the ethylene to effuse. Now, if you let it sit for an infinite amount of time, right? You let it sit for like a year, they're all going to fill up both spaces, and you would get that full effusion. Gas would fully expand to the new volume. But importantly, over a shorter time, the lighter molecule will effuse more quickly, and we use this to separate gas mixtures. This is how we separate gas mixtures. It doesn't matter what the gas mixture is. This is how we do it. Because otherwise, every other property is the same for all the gases, right? The ideal gas law says they all respond and change in different ways. It's all about this effusion. And so, when we're dealing with doing this sort of idea of separating mixtures using effusion. You could take your mixture in, say, right here. Let's switch to a different color. What's going on? So you take the mixture in, say, right there, and then you let it pass over some sort of barrier that just has holes marked in it, right? That's these lines right here. And so there's these barriers that have holes poked in them. And so those allow for the possibility of effusion. And so as the gas is just kind of bouncing along around here, those lighter molecules are going to effuse more quickly, so more of them make it out. And then the heavy molecules stay inside. They don't pass through because they effuse more slowly. So because their molecules only go past these barriers for a certain amount of time, more of the small molecules make it out, and more of the heavy molecules stay inside of this, right? So they stay inside of that. And so this process doesn't work perfectly. Because it's a gas, everything's all random. Not all of your light molecules escape, and not all of your heavy molecules stay in, right? So you don't get perfect. But what you do is you basically just repeat this process over and over and over again. You get this enriched stream where you get a little more of the percentage-wise, you get a little more of the light gas. And then you do that over barriers, and again, you enrich it a little more, you enrich it a little more. And so any sort of gas separation that we do has to rely on these ideas, rely on these mechanisms that just do this over and over and over again. So one main process or main application of this is separating isotopes, right? We said that when it comes to isotopes, all of their chemical properties are the same, right? If you have, for example, uranium-238 and uranium-235, they're both uranium, so they have the exact same chemical properties. They do all the exact same chemical reactions. So you can't separate those isotopes by doing some sort of chemical process. Instead, you need to do something based on their different masses. And so what you do is you take those uranium atoms, you get them into a gas. In this case, you can form a molecule with 6 fluorine atoms, so uranium hexafluoride. And so the different isotopes do have slightly different masses. As a result, they will effuse at slightly different speeds. So the slightly lighter one, which corresponds to the smaller isotope, effuses, the ratio of fusion is 1.0043. So 0.43% faster, okay? So if you take your mixture of, you have both isotopes in, you bring them together down here, it will preferentially that the light isotopes will pass through the barrier, and it will be more heavy isotopes going down here. This cartoon makes it look like all of those light green molecules, you just get a huge amount of differentiation. But again, it's 0.43% faster, so you get barely any enrichment per time that you pass across a membrane, right? You pass across a membrane with those kind of holes poked through it, and you get some gases that go through there. Some enrichment that goes through there. So what ends up happening is you do this a lot of times. So back in the 1940s, if you want to isolate uranium for use in, say, nuclear energy or nuclear bombs, you need to have more uranium-235. And so what they did was the plan was just do this 4,000 times. So you would put in your uranium sample and you would run it over 4,000 membranes. So you need a bigger facility to do that. So they built the city of Oak Ridge, Tennessee. So this is, you can see there are these are this is like a forest back here, right back here. That's a forest. To give you a context, these are huge buildings. This is a massive facility. This, for example, is a river. So these are huge facilities that they were using to just kind of brute force get the separation. Because when it comes to separating isotopes, this is really what you got to do. And in the case of uranium, it's just a tiny difference that they're having to rely on to get that much higher level of the uranium-235 isotopes that was necessary in order to use those nuclear applications. And we have slightly more efficient techniques today. It's just smaller size. We're still relying on effusion, so you're still relying on the same principles to do that idea that lighter molecules just diffuse more quickly. That's one of the only differences for isotopes. So this is how you separate isotopes. And we do this for not just uranium. Anytime, if you want to get only one isotope of a given element, that's how you do the separation.